If you take a gas under high pressure, so a dense gas, okay, and you heat it or subject it to a high voltage, it starts to glow. That's what the sun is. The sun is dense gas under high pressure, okay, energized with heat. You can also do this with energized solid, so hot metal, for example, or liquid, like that molten metal there. Now, if we take this glow, this light being emitted from these bodies, and we pass it through a slit and a prism, we get this rainbow spectrum that you're all familiar with. And we know that there are colors above and below the spectrum that we can't quite see, the infrared series and the ultraviolet region as well. The infrared region, I mean. And we recall that this is the low frequency, low energy portion of the spectrum, which happens to correspond also with a long wavelength. So these are long wavelengths, but low frequency, low energy. And over there we have the shorter wavelength, but higher frequency and higher energy. So wavelength is a distance between successive crests. Hopefully you remember that. The important thing though about this picture is that what we're looking at here is a continuous spectrum, which means it contains basically all the wavelengths without any gaps. What we're going to focus on though in this video is something called a line spectrum. And to create a line spectrum, what you do is you take a low pressure gas instead of a high pressure dense gas. Okay? In this case, we're going to use hydrogen. And you put it in some kind of container. Here we call this a gas discharge tube. Not too important for now. Okay? And again, we energize it either with high heat or with high voltage. Here it's being energized with a high voltage, a high voltage being passed across those wires. It also starts to glow, just like the previous example. But this is a different kind of light. Because if we take this light, we pass it through a slit and a prism, instead of getting that continuous spectrum, we get this weird series of lines. The order is still preserved, so we still have the low frequency, low energy at one side and the high frequency, high energy at one side. So for example, red is lower energy than those violet colors there. Okay, but most of the spectrum is gone and we're just left with a series of lines. We also notice that for these lines, the distance between them seems to be getting successively smaller or progressively smaller. Okay, now these are the lines we can see, but if we had sensors that could detect ultraviolet and infrared light, we would also notice that this pattern, this converging pattern, is repeated once in the ultraviolet region of the spectrum and several more times in the infrared region of the spectrum. What do these lines mean? And what can they tell us about the structure of the substance, in this case hydrogen, that is creating these lines? Scientists have been thinking about this question for a long time. One of the first people to put some good mathematics to it and come up with a satisfactory or somewhat satisfactory explanation was that guy there, Niels Bohr, pictured here at the, I think this is the Solvay conference in 1927 with a bunch of other chemistry and physics hotshots. What Bohr proposed was a system of what are called quantum orbits. Okay, here's the idea. Hydrogen's one electron here. You know hydrogen consists of just a proton and an electron, right? That one electron can exist in a number of converging orbits. Okay, we call them n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and they go on, but they get closer and closer together, eventually converging at what we call n equals infinity, which of course infinity doesn't quite exist, but you get the point, right? They get smaller and smaller together, converging to some point. Okay, this is somewhat similar to a planetary or solar system model where you have the sun and you have the planets orbiting that sun, right? What Bohr did was he used some fancy mathematics to calculate what these distances would be expected to be. Okay, and we'll see that those distances that he calculated ended up to be quite correct. Okay, so what Bohr suggested then is that as we energize this hydrogen gas, this electron can jump to successively higher orbits. Okay, so we energize it and the electron jumps to a next orbit. We energize it, it jumps to a next orbit, and on like that. Okay, and it can also fall down to lower orbits. And when it does, it releases photons of a specific frequency. And the larger the drop, the higher the energy of the photon that is released. Okay, we can also jump more than one level, and we can fall down as well more than one level. Again, the important thing, as I just said, is that the greater the distance of the fall, the higher the energy of the photon that is emitted. Okay, Now, an important thing to note here is that the electron is moving instantaneously from n to 1, from n of 1 to n of 2, and to n of 3 like that. It doesn't actually pass in the space in between, which is kind of a crazy concept. Imagine if you had a car that went from 0 miles per hour instantaneously to 20, and then to 40, and then to 60. You never went in between those speeds, okay? The reason it's possible is because we think of the electron actually as a wave when we're thinking about these orbits. You don't have to really consider that for now. But here's a question based on what we've said so far. Pause and think through it. We're asking which of these would emit photons of a few specific wavelengths. That is a line spectrum as opposed to a continuous spectrum. Again, pause and think. In 3 seconds, I'll show you a clue. 1, 2, 3. There's your clue. In 3 seconds, I show you the answer. 1, 2, 3. There's your answer. Okay? All right, so let's get back to it. How do these transitions, right, these transitions of electrons we just mentioned, how do they explain the emission line spectrum of hydrogen? This again is what Bohr was after. Here's the idea. Well, here's the spectrum. Now let me ask you a question about the spectrum. Which of these lines in that spectrum are the highest energy lines? Pause and think. Which are the highest energy lines? It should be obvious. It'd be that series there in the ultraviolet region. We call that the Lyman series. And now here's another question for you. Which of the, wait, what's this? It says, which are the largest electron drops or downward transitions? So what are the largest possible electron drops downwards like that? It must be into n equals 1, right? You can think of n equals 1 as the lowest possible state, okay? So the largest energy drops would be drops down into here, maybe from there to there or there to there, and so on and so forth, right? Okay, so here's the idea then. The idea is simply that drops into n equals 1, which is the lowest energy state, produce emission lines in the ultraviolet region of the spectrum, called the Lyman series, as I said. So drops into n equals 1, that is drops as low down as possible, would produce a high energy sound, you can think, or high energy frequency of light. For example, n equals 2 to 1 will be that line there. Then 3 to 1 will be the next line. 4 to 1 is the next one. 5 to 1 is the next one. 6 to 1, 7 to 1, and so on. Importantly, we can keep going 8 to 1, 9 to 1, 10 to 1, but those lines begin to merge into a kind of continuum, difficult to tell apart. We call the limit after which they merge the convergence limit. Okay? We'll talk a bit more about that in a second. Now, the important thing, or one important thing, is that the distances that Bohr had calculated exactly match the distances between those lines in the emission spectrum, or they don't match it, but they're proportional. Okay, so Bohr's model was quite correct, at least for hydrogen. Let's actually try and animate what's going on for the Lyman series so we can understand it in a bit more depth. So here's the idea. Again, a reminder that photons are light packets, okay, and they're going to be emitted when electrons fall down to lower energy levels, right? And we're going to direct these photons to this prism somehow, okay? And finally, another important thing is that the photons will be bent based on their frequency or based on their energy, okay? The order is that lower frequency photons are bent less, but that's not important for the IB. So let's try and see what happens. So, okay, and we're going to see what's going on that measurement apparatus there. Okay, a quick reminder: we're going to put the lower frequency, lower energy, but longer wavelength lines towards the bottom, and higher frequency, high energy, shorter wavelength towards the top. So here's the idea now: is that we energize the electron. It jumps, let's say, just by chance to n equals 2. And then when it falls down from n equals 2 to 1, it releases a photon of light, which creates that line there. Okay? Then we energize it again, and it goes this time to 3. It falls down. We produce a line again on the spectrum. Then n equals 4 to 1. We produce another line. And you see now the lines are getting closer and closer together because these falls are getting less and less different. Okay? Then next up we have 5 to 1, which is another line there. 6 to 1, which would be another line getting closer and closer together. 7 to 1, we keep going. And then we can imagine that if we just keep going on and on and on, these drops get closer and closer together. We can imagine then the electron dropping from very close to n equals infinity, right? Because you can never quite get to infinity. But when it's close to n equals infinity, it's basically has left the atom, okay? And that is basically going to be the highest energy drop possible. And that highest energy drop will correspond then to what's called the convergence limit. That convergence limit corresponds to this distance here from n equals infinity to the ground state, or n equals 1, which is the lowest energy state. So that was just an overview again of how we get this Lyman series from drops into n equals 1. Now what about the other series? Well, it should become obvious what's happening. Drops into n equals 2 will then produce the emission lines in the visible spectrum. We happen to call these the Bohr series. Again, that's vocabulary that the IB will not hold you responsible for. Okay? An important thing, though, is that only the first 4 transitions are visible to the human eye. So only these first 4, 3 to 2, 4 to 2, 5 to 2, and 6 to 2, produce light that is in the visible region of the spectrum. The others, 7 to 2, 8 to 2, 9 to 2, and so on, actually slip into the ultraviolet region. So they're a bit too high energy for us to see those photons of light. Okay? This is more or less the most important part of this presentation, so I think it deserves a jingle of its own. So let's try that. Electron drops into n equals 2, produce light in the visible spectrum. 3 to 2, 4 to 2, 5 to 2, 6 to 2. Electron drops. All right, you can go several times if you want. So those were drops into n equals 2. How about drops into n equals 3? Those would produce light there in the infrared region of the spectrum. We happen to call those the Paschen series after the guy who worked on them. You don't have to remember that. And then on, you have the bracket series into n equals 4, and then a bunch of other series, which we don't think about for the IB. We think basically about those first 3 series, and we don't have to remember their names or the people who worked on them, the Paschen and Lyman stuff. Okay, an important thing is that the drops into n equals 1 release higher energy than all of the drops into n equals 2. So all drops into 1 are higher energy than all drops into 2. Let me show you what I'm talking about with this next picture. So as you can see, it's pretty clear that all the purple lines are higher energy drops or longer drops than all the blue lines, which are longer drops than all the red lines. So for example, 2 to 1 is a higher energy drop than like 9 to 2, for example. Okay? And because of that, all of the transitions down to 1 are higher energy on the spectrum, higher frequency on the spectrum than all the transitions into 2, and so on and so forth. That's an important thing that the IB might hold you responsible for. Some important vocabulary that it's nice to look through in a detailed fashion. Convergence describes the phenomenon where within each series, spectral lines tend to get closer together at higher frequencies. Within each series, spectral lines get closer together at higher frequencies. Within each series, spectral lines get closer together at higher frequencies. It's pretty obvious what's happening there. The reason, of course, is that the energy levels also start to get closer together, start clustering together at higher energies. And so the spectra mirror the energy levels, or the lines on the spectrum mirror the energy levels. Another important point is the convergence limit is that point beyond which the spectral lines merge into a continuum. Okay? And it represents basically the energy of that electron dropping from n equals infinity down to n equals 1. Another important piece of vocabulary, the ground state, I've used this term a few times, is the lowest energy position for an electron. For hydrogen, it's n equals 1. For other electrons in other higher electron atoms, it might not be n equals 1. And we have the excited state, which I've canceled out here, is not the ground state. So anything above the ground state. Based on this, let's try and answer now some questions. Here's a question for you. Outline how the spectral lines in the visible region of the hydrogen emission spectrum are created. This is the kind of question you'd get on paper 2 of the IB. Pause, think about how you would answer it, and then in 3 seconds I will show you my answer. 1, 2, 3. There is my answer. I draw the actual emission lines, okay, show how they correspond with the energy levels, and explain it in a few short points there. Another question for you. In the emission spectrum of hydrogen, which of the following transitions produces a line visible to the human eye? Again, pause, think about it. In 3 seconds, I show you a clue. 1, 2, 3. Again, pause, think about it. In 3 seconds, I show you the answer. 1, 2, 3. Pause again if you want to process that. Another question. Which of the following is true and is evidence that the electron energy levels are discrete, not continuous? Pause again. Pausing and thinking is the best way to learn. 1, 2, 3, I show you a clue. 1, 2, 3, I show you the answer. There you go. Pause and read through that. Now you might have some questions for me. One question you might have is the following. Why are we going on and on about hydrogen when the real question is whether Bohr's model, the whole transition thing, explains the emission spectrum for all elements? Here's the spectrum of hydrogen. It's quite simple to explain. How about helium? How about neon? How about all the other more complicated spectra that come after hydrogen? Why are we focusing just on hydrogen? Well, the reason is that Bohr's model only explains hydrogen's emission spectra. Okay? It also explains spectra for other what we call one electron systems. That's higher level. You don't have to think about that at the moment. To explain these more complicated spectra, we'll need something called orbital theory, which we will discuss in a future video. Another question you might have for me is the following. We've said that if you take a low pressure gas and you energize it, and you pass that light through a slit, a prism, you get an emission line spectrum. And that emission line spectrum, we had said, is explained by thinking about the energy levels in the atom, or in the hydrogen atom in that case. Okay, so basically the electronic configuration of that atom. But for some reason, if we make it a dense gas, a liquid or solid, and we make that glow by heating it up somehow or passing a high voltage, we get this time a continuous spectrum. So why is it only low pressure gases that produce these line spectra? Aren't these guys also made up of atoms which have energy levels as well? Why don't they also produce line spectra? It's a long story. You don't have to think about it for the IB, like many of the things I say here. But what you can think is that there is an underlying line spectrum, okay? But it basically gets smudged by the density of these substances, okay? It is basically blended or smeared into one continuous spectrum by the density, okay? But again, that's just extracurricular knowledge for you. So now we have talked about emission line spectra. Let's get to absorption line spectra, another thing you will be held responsible for on the IB. So we had said that if you take an energized dense gas, liquid or solid, anything dense basically, you take the light that is emitted from it when you heat it up or pass a high voltage through it, you pass that light through a slit and then a prism, what you get is that continuous spectrum there. On the other hand, if you take a low pressure gas and you energize it, you get the line spectrum. Finally though, you could take continuous spectrum light like that, okay, and pass that through a cold non-energized gas. Again, in this case, we're using hydrogen. What you get though this time is something that looks like that. So each of the emission lines is mirrored in this absorption line spectrum, but it's kind of flipped. Here we have a dark line against the full spectrum background. Okay? Now again, like I said, this perfectly mirrors the emission line spectrum of that particular element, in this case, hydrogen. How do we explain this absorption line spectrum here? Well, recall the explanation of the emission line spectrum. We had said that as electrons drop from higher to lower energy levels, they release photons or packets of light of specific wavelengths, of specific frequencies. And those are separated out there on that piece of photographic film or that sensor there. Okay? But the question is, how do those electrons get promoted in the first place? How do they jump up to higher energy levels? In the gas discharge tube, we had promoted them by adding energy in the form of a high voltage. We can also add energy in the form of light. Okay? So if we add light in here, then the electron can absorb light of specific frequencies and jump up based on the frequency it absorbed. So if it absorbs light of that frequency, it jumps up 2 to 6. Okay, that's high energy light. Okay, next up we have 2 to 5 absorbing light of that frequency, 2 to 4 there, and 2 to 3 that lower frequency there. Okay, and remember that we're going to have billions of hydrogen atoms in this sample, and so somewhere in there there'd be some electron that's willing to accept that specific wavelength of light in order to jump from 2 to 3. Willing to accept. Okay, now it makes sense, therefore, that the absorption spectra are mirror images of the emission spectra. Why? Because whatever frequency is used on the way up is basically pushed back down or pushed back out on the way down. Here's another visualization of that idea here. Here, this electron is jumping from 2 to 4. It absorbs this green wavelength, okay, therefore creating that absorption line on that spectrum there. And when it's dropping down, then we create the emission line there. So that's the relationship between the absorption and the emission line spectra. Here's another picture showing you the same thing. This one perhaps might be easier to draw or represent somehow on the exam. You can see basically that the electron drops produce lines on the emission line spectrum that mirror the lines that are absorbed on this absorption line spectrum as the electrons jump to higher and higher energy levels. This is, of course, here the Bohr series, which is drops into or transitions out of the n equals 2 shell. Okay. And now let's look at some questions based on what we have done so far. So here's a question for you. This diagram illustrates several electron transitions for an element in the hydrogen atom. I want you to read through all of these and indicate what transition they correspond to. Pause and think about it for however many minutes you need. But in 3 seconds, I will show you the answer here. 1, 2, 3. There you go. Okay, here's another question you might get on paper 2. Distinguish between an absorption spectrum and an emission spectrum for 3 points. Pause and think about how you would answer this. In 3 seconds, I will show you the answer. 1, 2, 3. There's how I would answer it. Finally, we have another one here. Distinguish between a continuous spectrum and an emission line spectrum. Pause again, think about those distinctions. In 3 seconds, I show you my answer. 1, 2, 3. There we go. Okay? So basically now we have discussed how continuous spectra are formed, how line spectra are formed, but we said there are 2 types of line spectra. There's the emission line spectrum and there's the absorption line spectrum. And we've talked about how these spectra are related to electronic transitions in that Bohr quantum orbit model. In a future video, we're going to discuss the fact that Bohr's model does not explain the emission line spectra for elements above hydrogen. And so we're going to need another model called orbital model, the orbital model, as opposed to the orbit model. Okay, and for that orbital model, I will see you in a future video.